Every year, humanity extracts more than 4 billion tons of crude oil, a colossal volume large enough to submerge the entire island of Manhattan beneath a layer of oil nearly 80 meters deep. But to obtain every drop of that oil, humans must overcome one of the greatest engineering challenges of the modern age: locating oil fields buried deep underground, drilling through rock formations thousands of meters thick, building massive drilling rigs in deserts and oceans, and then moving the oil through a vast network of transportation and refining systems that spans the globe. Join Factron process as we explore how humans conquer the earth and the oceans, all to extract the liquid that helps power the global economy. Oil is not just fuel. It is one of the resources that has helped shape the modern world. The global oil and gas industry generates around $7 trillion in revenue each year, equivalent to nearly 7% of the world economy. What is remarkable is that this resource originated from microscopic marine organisms that lived more than 100 million years ago. Under the effects of heat and pressure deep within the Earth, they gradually transformed into hydrocarbon deposits buried beneath the planet's surface. A significant portion of the world's oil reserves is concentrated in the Middle East, especially in Iran, Iraq, and Saudi Arabia, making the region a focal point of geopolitical competition for decades. Meanwhile, the United States chose a different path, extracting shale oil through modern technology, giving rise to the famous slogan,
"Drill, baby, drill."
The journey to find the black gold that powers the world does not begin with giant drilling rigs. It begins with something invisible: sound. To avoid gambling tens of millions of dollars on random drilling attempts, geologists must effectively ultrasound the Earth. On land, they deploy fleets of heavy specialized trucks known as vibro-size vehicles. Instead of digging into the ground, the vibro-size hydraulic piston system repeatedly drives a massive steel plate against the surface, generating forces of up to 60,000 pounds, equivalent to the weight of a large truck concentrated onto a single point. This force sends sound waves with frequencies ranging from 20 to 150 Hz through rock formations buried as deep as 15,000 feet beneath the surface. As these waves encounter different geological structures, they reflect back toward the surface and are captured by a network of tens of thousands of sensors. Using this data, supercomputers construct detailed 3D maps of the subsurface geological structure. Once the first drilling location has been selected, field operations begin immediately. In just a few days, more than 1 million pounds of equipment can be transported to the site, including the drilling derrick, drilling mud systems, and large power generators. Heavy cranes lift steel components into the air one by one. The oil derrick rises to a height of more than 140 feet, equivalent to a 12-story building, becoming the most prominent structure in an area that was little more than empty land only days earlier. Beneath the derrick, dozens of engineers and workers continue installing electrical systems, high-pressure pumps, and control equipment. Every connection must be carefully inspected before operations begin, because the drilling campaign that follows can cost anywhere from $5 million to $20 million. Once the final preparations are complete, the drill bit is ready to begin its journey into the Earth. 30-foot steel drill pipes are connected together and lowered into the ground, carrying a specialized drill bit at the bottom. This is no ordinary drill bit. It is a PDC, polycrystalline diamond compact bit, whose cutting surfaces are fitted with synthetic diamond cutters mounted on an ultra-hard tungsten carbide substrate. Under a compressive force of 50,000 pounds and a rotational speed of 150 RPM, the system does not excavate rock in the conventional way. Instead, it directly cuts through and pulverizes some of the hardest underground rock formations. To prevent friction temperatures that can exceed 1,500 degrees Fahrenheit from damaging the equipment, high-pressure drilling mud is continuously pumped to the bottom of the well to cool the bit and carry rock cuttings back to the surface. Depending on geological conditions, an exploratory well may need to reach depths of 10,000 to more than 20,000 feet before reaching the target formation. In fact, the deepest borehole ever drilled, the Kola Super Deep borehole in Russia, reached a depth of more than 40,200 feet. Once the planned depth is reached, engineers lower gamma scanning tools into the well to determine whether the formation below contains oil, gas, or simply salt water. This is the moment of truth. Will this location become a commercial black gold field, or merely an empty hole that burns through $50 million in investment? Finding oil is only the beginning. To turn that discovery into a productive well, engineers must complete its structure and create pathways for the oil to escape from the surrounding rock. In conventional fields, wells are usually drilled vertically into porous sandstone formations. For shale oil, the drill is steered horizontally for another 1 to 2 miles to increase contact with the reservoir. Steel casing sections approximately 40 feet long are then lowered into the well, while high-pressure cement is pumped around them to stabilize the structure and prevent leakage. A perforating tool creates hundreds of openings through the casing and cement, allowing oil to enter the wellbore. In conventional reservoirs, natural pressure may push the oil through these openings. In dense shale, however, millions of gallons of water, sand, and additives are injected at pressures exceeding 10,000 psi, creating thousands of fractures that release the trapped oil. Once oil begins flowing into the well, the next challenge is lifting it from depths of thousands or even tens of thousands of feet to the surface. During the early years of production, many oil fields possess enough natural reservoir pressure to push oil to the surface on their own. However, reservoir pressure gradually declines over time. When that happens, one of the most recognizable symbols of the oil industry begins to appear: the pump jack, also known as the horsehead pump or donkey pump. This machine, weighing between 20 and 40 tons, operates like a giant surface pump. Every minute, the pumping unit continuously nods up and down between 5 and 15 times, pulling a string of steel rods thousands of feet long beneath the ground to lift oil in successive stages. Each stroke raises a small amount of oil closer to the surface. Thousands of strokes, operating day and night, week after week, gradually drain the underground reservoir, lifting between 20 and 300 barrels of oil per day to sustain the entire project. Bringing oil to the surface is an achievement, but keeping the system from being overwhelmed by underground pressure is a matter of survival. Throughout the production life of the well, engineers must continuously monitor pressure, temperature, and flow rates inside the well to ensure that oil production remains stable and under control. If pressure exceeds 10,000 psi or the flow becomes unstable, a major incident can occur within minutes. At that point, the blowout preventer, BOP, becomes the last line of defense. This massive steel assembly can weigh more than 300 tons and is powerful enough to clamp shut and seal the entire well in less than 30 seconds, preventing high-pressure oil and gas from erupting uncontrollably. The importance of the BOP became evident to the entire world after the Deepwater Horizon disaster in 2010. When this offshore oil well went out of control, the resulting explosion killed 11 workers. Oil then continued to spill into the ocean for 87 consecutive days, releasing nearly 5 million barrels of oil into the Gulf of Mexico and becoming one of the most severe environmental disasters in the history of the oil industry. The fluid brought up from a well contains not only oil, but also natural gas, salt water, and mineral residues. At the field, this mixture enters separator vessels up to 40 to 60 feet long, where it is divided by density. Gas rises to the top, water and solids settle at the bottom, and crude oil remains in the middle. In mature fields, each barrel of oil may come with 3 to 10 barrels of water. The gas and water are treated or re-injected underground to maintain reservoir pressure, while the oil is desalinated before entering pipelines or tankers. Commercial-grade crude oil leaves the field through pipelines or by sea. On land, millions of barrels move each day through pipeline networks powered by booster stations. Across oceans, the oil is carried by VLCCs more than 300 meters long, each capable of transporting 2 to 3 million barrels. This scale also brings major risks. In 1989, the Exxon Valdez ran aground in Alaska, spilling about 260,000 barrels of oil and contaminating more than 1,300 miles of coastline. Disasters like this led to stricter monitoring systems and modern double-hull tanker designs. Crude oil is almost unusable in its raw form, but once refined, it can become fuel, plastics, clothing, cosmetics, and thousands of other products. At the refinery, crude oil is heated to around 650 to 750 degrees before entering a distillation tower up to 60 meters tall. Hydrocarbons are separated by boiling point. LPG and naphtha rise to the top, kerosene is collected in the middle, while diesel and heavier fractions remain below. The heavy fractions are then sent to cracking units operating above 900 degrees Fahrenheit, where large molecules are broken into lighter ones to produce more gasoline, jet fuel, and diesel. If engineers on land only have to drill through rock, offshore they must first conquer an entire ocean before reaching the first layer of rock. Instead of building drilling rigs on the ground, engineers operate drill ships or floating drilling rigs that can stretch hundreds of meters in length. While onshore wellheads and control systems are located at the surface where engineers can access them directly, offshore systems are often installed on the seabed at depths ranging from more than 1,000 to 3,000 meters. At these depths, water pressure can exceed 300 times atmospheric pressure, making direct human intervention nearly impossible. Instead, all operations are entrusted to ROVs, remotely operated vehicles. These machines can carry cameras, sonar systems, and hydraulic manipulators to operate valves, install equipment, and repair subsea pipelines. In many modern offshore fields, ROVs are virtually the only workers operating at such extreme depths beneath the ocean. The oil is then gathered through a network of subsea pipelines and transported to FPSOs, floating production storage and offloading vessels, more than 300 meters long, for processing, storage, and preparation for transportation. To extract oil from beneath the ocean floor, humans did not simply build a drilling rig. They built an entire floating industrial ecosystem in the middle of the sea. From invisible sound waves penetrating deep beneath the earth to wells drilled more than 20,000 feet into the ground, the journey of oil extraction represents one of the most complex engineering achievements ever created by humanity. Every barrel of oil is more than just fuel. Behind it are machines weighing hundreds of tons, robots operating thousands of meters beneath the ocean, and industrial systems stretching across continents and oceans alike. What begins as organic matter buried millions of years ago eventually becomes gasoline powering vehicles, jet fuel carrying passengers across oceans, plastics used in everyday products, lubricants that protect engines, asphalt that covers roads, and countless materials that support modern civilization. Before reaching consumers, crude oil must pass through exploration, drilling, pumping, transportation, refining, quality control, and global distribution systems, each step requiring precision, safety, and enormous investment. Few resources have shaped the world economy, transportation networks, military power, industrial development, and daily life as profoundly as oil. It connects remote deserts, offshore platforms, refineries, ports, pipelines, airports, factories, and cities into one massive energy network operating every hour of the day. If this journey surprised you, be sure to subscribe and join Factron Process for future industrial journeys. And let us know, which technology in the oil industry impressed you the most?